All right. In this video, I want to kind of talk about a couple of things that are in the notes that I could not find like really great explanations for online that didn't also include other things. So if you have not already gone ahead and watched the videos that are in the rest of the videos that are in the homework playlist, specifically part 1, what is the gradient vector? Okay, that's what this section is about. And the gradient vector is actually super important going forward. So if you've not already gone ahead and watched part 1, which is about the gradient vector, and then part 2, the gradient and level curves and the gradient and graphs, that's important to kind of thinking about these first couple of examples when I'm trying to illustrate by making you graph one level curve, making you graph a little bit of a contour plot, and then draw the actual gradient vector. So watching the gradient and level curves video will help you kind of think about these first 3 examples. But one application, before we move on to something even better, one application of the gradient and level curves and the gradient and graphs is that this gradient vector that we're creating is actually a normal vector. It is a vector that is normal to our surface. This is super helpful for the application that what we just covered in 13.4, which was writing the equation of a tangent plane. And that's what I wanted to show you here. And then I'll show you something else. Okay, but first, we're going to do a little proof. Like, why does this work? And this is a little bit of a little bit less mathematical, a little bit more verbal. That doesn't mean it's not mathematical, it just means it's less formulaic. So the chain rule is going to be key to our proof. So again, if you're watching this and you kind of skipped over 13.5, go back, watch it again. So what's important is we are going to take take a curve, and we're going to make it a vector curve. We're going to R of t that is contained in the level surface. And here we have some kind of function over here. We've got f. So we'll have, you know what, we'll just call it, I'll say my function is w. So we're going to have w equals c. Okay, so where w is a surface. So, yeah. Okay, so one thing that we know already, and here let me actually just draw a little picture. And this is in the filled notes if you want to follow along. Okay, but there are my axes, and then I'll make like a level surface. We'll just like do a little magic carpet surface here. Okay, so that's W. Okay, W of X, Y, and Z, and I'm setting it equal to C. Okay, we are taking a curve, which we called R of t. That R of t is contained in that surface, meaning it's always going to be in there. Now, one thing we know is that the velocity vector or the derivative vector, so dr dt, which is, we'll call it v of t, is tangent to r of t all the time. Okay, that makes sense. It's the derivative vector. So I will illustrate that using a little bit of purple here. Okay, so my vector, okay, it's like just tangent at that point. Doesn't have to be tangent always, remember. Okay, so that's my velocity vector. So if it's that v of t vector is always tangent to the curve that is contained entirely in the level surface, then that v of t, okay, so therefore, v of t is also tangent to the surface. Okay, that's cool. Awesome. Okay, but now what we would like to define this as, okay, we can actually, since this is and maybe I should make this a little bit more clear, my R of t, okay, since we are in a surface, a three-dimensional surface, that will be some x of t, y of t, z of t, okay? So now using our chain rule, if I want to find the derivative of the surface with respect to t, okay, that would be, as we proved, the gradient vector dotted with r prime of t, or if you want to write it better, gradient vector, okay, dotted with v of t, okay? But here's the thing, okay, we're in a level surface, but since we have w equal to a constant, we're in a level surface, that means that the rate of change of w with respect to time should be 0, which means 0 equals the gradient of w dotted with r prime of t. Okay? That means that our gradient vector, okay, if the dot product of these two vectors is equal to 0, our gradient vector is going to be orthogonal, and maybe I should be a little bit more consistent on my notation here. Which one am I choosing? Our gradient vector will be orthogonal to the derivative vector at all times, okay? But this is great. This is true for any vector tangent to a surface, okay? So our big conclusion is, and I'll write it over here, don't worry, okay? Our gradient vector is orthogonal to any vector tangent to the surface. That's super important for writing a tangent plane because, as you can see in this diagram here, if I'm trying to write the equation of this tangent plane, which I will highlight in yellow, I want the equation of that tangent plane. What I need, okay, is, well, it's the equation of a plane, so I need a vector orthogonal to that plane, okay? And I can find that by using vectors in the plane. Well, vectors in the tangent plane are vectors that are tangent to the surface. Okay, so this is really important. Our big conclusion here, what that little proof was just showing us, that for any surface, any level surface, and in fact, if you look back at these examples in the field notes, for any level curve, our gradient vector is going to be orthogonal. That allows us to use the gradient vector as our normal vector for any tangent plane. Okay, so let me show you, just walk through example 4, how that makes this so much easier. Okay, so we could have a surface that looks like this. Okay, think about what surface that might be. And we want to find the tangent plane at the point. Maybe we want to do like a linear approximation. Now, what we could do is we could solve for z, and that's how we were doing it in 13.4. We were solving for z, we were taking some partial derivatives, blech, okay? But if instead we change our mindset a little bit and we think about, instead of this being like having to solve for z and then writing that as a function of x and y and then taking partial derivatives, if we think about this instead, if we think about this instead as some level surface for a function of x, y, and z, okay, so instead we're thinking about it as a level surface for a 4-dimensional function. Do you see where I'm going? Okay, then we can use this kind of gradient vector application instead. So what I'm saying is, okay, now we have w equal to x squared plus y squared minus z squared. Okay, and like I did in the proof, I let w equal 4. Now, if I want to find the tangent plane, all I need to do is take the gradient of w, which is a vector. It will be partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Now I'm looking for it specifically at the point 2, 1, 1. So I want gradient of w at 2, 1, 1, which will be 4, 2, negative 2. Okay, and then I've chosen a point. This is my normal vector. we're already done. I have a point, I have a normal vector. All I have to do is put it into the equation of a plane. Okay, the tangent plane is 4x minus 2 plus 2y minus 1 plus, minus z minus 1 equal to 0. Remember, don't forget the format of your plane. Okay, so I wanted to show you that one application of the gradient vector first. In the next quick video, I'm going to do more applications of the gradient vector using it to find a directional derivative.